Guys, we're just going to try and go through basically what I did with the other students in the double, and that is we're going to start with the covalent bonding because we finished off with ionic last time. Now I'm going to be focusing more on difficult types of questions. So what I want us to do is actually see if we can remember how to write out the electron dot diagram and the valence structure. Okay, so just starting off with that type of thing. Now I'm not going to tell you how many of each atom you need. You need to work that out. You can work that out based on how many electrons it requires. But does anyone remember covalent bonding? Like, we wrote down what it's between. What's it between again? Non-metals, very good. So what do non-metals want to do usually? Gain or lose electrons? Non-metals. That's all right. They want to gain electrons. So we'll sort of start off with that. If you've got two things bonding together that want to both gain electrons, they can't really steal the electrons from each other, okay? So what do they actually end up doing in covalent bonding? They share. Isn't that nice? It's actually because they're really they're quite similar in electronegativity, so no atom is strong enough in electronegativity to take the electrons. So they end up sharing. So we'll do one as an example and then I'll get you guys to do another couple. So let's say if we wanted to look at phosphorus and chlorine bonding together covalently. Now, they're both non-metals, so we know it would be covalent bonding. Where might we start? No? Josh, how many electrons does phosphorus require to fill its outer shell? Grab your, do you have periodic tables? I want everyone to have a periodic table the whole time through this. Do you have one? Grab your periodic tables out. You guys can share that one. Okay. Yeah. Okay, so it's in group, what group's it in? 5. Okay, so if it's in group 5 and it needs 8 electrons, 5 electrons in its outer shell, what's it going to do? Hang on, so I'm asking Josh because the aim of this class is to make sure everyone understands it, yeah? So, Josh, if you look at the group number, yeah, as group 5, yeah, yeah. If you have a look at the group number, okay, you look at, let's say you're looking at oxygen. What group is oxygen in?
6.
How many electrons in its outer shell?
6.
How many electrons does it need to fill its shell?
2.
Oh, very good. 3 electrons is what it requires. Do you remember how many covalent bonds it'll make? If it requires 3 electrons, sorry? 3, yeah. So if something requires 3 electrons, it'll be grabbing 3 electrons from somewhere. Remember that it could be a double and a single. It just has to add up to having 3 altogether. If it gets 3 electrons from somewhere, it needs to also give 3 electrons to somewhere, meaning that these will be 3 bonds, whether they're a double and a single or 3 singles. Okay, so we've got 3 covalent bonds required by phosphorus. How many covalent bonds required by chlorine? 1. Right. So, Stacey, if phosphorus requires 3 covalent bonds, chlorine can only make 1 covalent bond. That's all right. Chlorine can only give 1 covalent bond. How many chlorines does that phosphorus need to bond to? 3. Very good. So you'll need to have 3 chlorines to that 1 phosphorus. And what type of bonds will they be? Will they be single, double, or triple bonds? Single, very good. Because chlorine can only make one, so it has to be a single. Okay, so you might want to put your phosphorus, that's your central atom, the one with the requiring the most number of bonds, in the middle. And then it has 5 electrons, but it's only going to be giving 3 to 3 chlorines. So it's going to have one pair by itself. Does anyone remember the name of the pair that's non-bonding? Lone pair. Okay, and then chlorine will have 7, even if I do it in another colour to make it a little bit more obvious. So chlorine will be 1, 2, 3, 4, 5, 6, 7. And chlorine over here. Okay, make sure they can see it. Okay, so then you might want to draw your circles in to show what's sharing and what's a lone pair. But your electron diagram will look like this.
Do we always have to do the circles?
You don't always have to do the circles. Just sometimes helps with finding which ones they're sharing, because it'll be like the Venn diagram. But if you don't need it, don't do it. Okay, then we've got a valence structure. Does anyone remember the difference between them? The lines, yeah. So how would I convert this into a valence structure? So one line is 2 electrons. Yep. So 2 electrons equals 1 line. So it should look like this. Okay, now we may also want to discuss its shape, molecular shape. Okay, to do the shape, we'll go through a little recap. Does anyone remember how to work out the shape or what the molecular shape is actually talking about? Yeah?
Number of bonds.
Number of bonds. Yep, so exactly. Then it talks about the shape between the atoms, so it only refers to the shape of the bonding electrons. It doesn't include the lone pairs, but the lone pairs may affect the overall shape. So 9 times out of 10, you'll be given these ones. So let's just say we've got 4 atoms surrounding a central atom. What type of shape would that be? Tetrahedral. Yep, so tetrahedral is when you've got 4 atoms surrounding a central atom. But let's say that you've actually got 3 atoms surrounding a central atom, but you've got 1 lone pair. Now you can't include that atom, in the shape. So we'll draw that out. So something like this, has the bond angle changed? This is 109.5, you don't have to do that. But has the bond angle changed? No, because it's still got that 4 regions of negative space around it that have to be as far apart as possible. Remember the toothpicks? But we don't have an atom here, so what do we call this shape? It's triangular. It's not planar because it's not all in the one plane. Pyramidal. Yep. Okay. Now, what if you remove another atom and you've got, we'll try and keep it the same. So what if we remove that atom? Do the bond angles change? Why do you reckon, Greta? Now the bond angles don't change again, because again, it's 4 regions of negative space. That's why you'd never call this linear. Even though you think, oh, but I can just draw it out like this. That's linear, isn't it? No. It's because when you think about it, remember when I gave you guys the toothpick thing and I was like, put all 4 toothpicks as far apart as possible, and a lot of you put it like a cross so that they were 90 degrees from each other. You can't do that because molecules are in 3D, so they can actually be further apart from each other than if you left them in the 2D. So it's not like that, even though you can draw it like that, it's still tetrahedral. These are not 90 degrees from each other, they're 109.5 degrees from each other. It's just hard to draw on a flat surface. Okay, so it's still bent or V-shaped. And then, if we remove, I've drawn this a bit differently, if we remove another atom, what does it become? Linear. So linear occurs when you've got, well, this has to be linear because it's only talking about between 2 atoms. But let's say you've got something like carbon dioxide. This is also linear. Why is this also linear? How many regions of negative space do you have surrounding that central atom? You've really got 2 because the bonds, the double bonds can't separate and go into a tetrahedral thing. They act as 2 separate regions of negative space. So they have to be, what would be the degrees here? 180. So it's linear. You've got to try and think about how many regions of negative space do you have. So, of course, what's this one then? All right, what's this one? Ooh, why is it not tetrahedral? Hang on, Stacey. There's no atom at the top. So you're only naming the space here. The shape, sorry, here. You're not including that top one because that's a lone pair. So what do you call it now, Stacey? Excellent. Triangular pyramidal. Okay, trigonal planar is if you've got 3 regions of negative space. So that's really common if you've got, like if you know your carboxyl group, COOH. This shape around this carbon is triangular planar, because you've got 3 regions of negative space, meaning that everything will have to be 120 degrees from each other, meaning that it will be flat on the page. So that's as far apart as possible it can be. So planar is, yeah, when it's in one plane. Okay, so did you want to do a couple yourselves of these ones? Just a couple of examples. Okay. And I'm not going to tell you how many of each. And what's silicon in the same group as? And sulfur? So this really limits my creativity in a way, because all I can ask you is like 5 different types. Okay? So say if I want to ask you something that's linear, I might go Si and S, Si and O, C and S, C and O, C and Se. But as soon as they're in the same group, same shape. Okay? Alright, so why don't you guys just quickly predict something that will have the same shape as PCl3. Yes? M? N and F3. Yep. It'll be exactly the same. Okay, so do you want me to just go through the other ones now? Yeah? Okay, so carbon and F, carbon needs but F can only give. So how many Fs do you need? Okay, so carbon will be your central because it needs the most, and F should be. And what type of bonds will these be? Single, double, or triple? So H and S. H and S, Sharika, how many does H need? And S? S can only give 2, yeah? So how many of which ones do you need? You need 2 of the H's. So it should be, we'll do it under valence. I'll just go straight to valence. Does that make sense? Guys, did you get that one? Yep, cool. All right, so let's just quickly do the shapes. So we said that that one was linear, just like carbon dioxide. How about CF4? Tetrahedral. How about HS? Yep. Did you say V-shaped? Perfect. Okay, so all good with that, guys? Yep. Okay, now what I was going to do is a revision on intermolecular bonding, because that was intra, this is inter. So let's just quickly go through intermolecular bonding. Did you guys bring your practice exams? You're so prepped. So intramolecular versus inter. Okay. Now with intramolecular, I'll draw it out and you guys tell me which one is. Okay, so in this diagram, which one is intramolecular bonding? Sorry? Think internet. What's internet versus intranet? Intranet is within. That's the thing that we use at the school. Yeah? So which one would be intramolecular bonding? This one? Yeah. Because when you say the O and the H, intra is always covalent. Because a molecule is always covalent. So that's fine. You only have to remember one for those. But the intermolecular is when it can get quite tricky. About that. All right, so intermolecular. You've got to first ask a question. Is it? No? Is it? No, but that's a type of intermolecular. First, before that, is it? No? Yes, but what's it called? If it's got one side, polar.
Polar, non-polar. Dipole, dipole, Gismondi.
No. You've got to ask if it's polar or non-polar. Now, if it's non-polar, it's easy. Because what holds the molecules together? Dispersion forces.
I remember this.
Okay, so if it's non-polar, it's only dispersion forces holding them together, and they tend to be the weakest type of intermolecular bonding. Yeah? So dispersion forces, though, can increase depending on something. Okay, first of all, what are dispersion forces?
It's when they bond and unbond.
Why would negative and positive repel?
I mean, negative and negative.
Yes. So you're saying the electrons in one atom can repel electrons in another?
Yeah.
Spot on. So, yes, it's like an instantaneous dipole. That's why you mean breaking and rejoining. Instantaneous, or you can think of it as a temporary temp dipole. Okay, it's when all of the electrons in an atom, by chance, it's not really all of them, but it's like if it's an uneven distribution of charge, okay, you'll get one side, let's say these are the electrons. Greta, what charge will this side be? If these are electrons. Yeah? So it'll be slightly negative. Yeah? And this side will be slightly positive. Why will that side be slightly positive? It's lost electrons, not completely taken away, but they have shifted to another side. So it used to be neutral, now electrons have moved away from it, making it slightly positive. And this is slightly positive, slightly negative, and then this can bond. Okay? Now, if we have loads more electrons, what happens to the charge, the delta negative charge?
It's stronger.
Yeah, so we get this larger delta negative. So, which bond's stronger? This or this bond? The larger one, because think about it like a magnet. If you've got two magnets this size attracting each other versus two magnets this size attracting each other, which one would be easier to pull apart? The smaller ones are easier to pull apart, meaning less energy is required to break it, meaning it's a weaker bond. It's just like that in dispersion forces. More electrons, you get stronger bonds, higher boiling points. So, increase when the number of electrons increases. Okay, so then if it's polar, there are a couple of types of bonds that it can make. Yes. So what do you ask yourself if once you know it's polar? But how will you know? If it's not, be too late. I've already said it. It's coming back. NOF bonded to H, that's hydrogen bonding. And then this is just dipole-dipole. So this is the strongest intermolecular bond. Okay, what I want you to do is determine which of the following, determine the type of intermolecular bonding in the following or type of intermolecular bonding between the following molecules. Okay. I'll just choose a whole range of them. Don't say anything. Bring in one that you've done before. And then we'll do a really tricky one. Okay, you may want to draw, I'd suggest that firstly you draw the valence structure, and then secondly do you remember that each bond is like a tug of war of electrons? So you have to, so just treat each bond as tug of war of electrons, and then in the bond, do you remember which one gets the delta negative charge? Oh, about the thing. No, that's fine. Do you remember which one gets the delta negative charge? It's not the one with the most electrons. The one that's the most electronegative. Because think about it, if it's a tug of war and you've got something, what's electronegativity again? How much they attract electrons. So, the most electronegative element that is closest to fluorine will pull electrons closer to it and become delta negative. Okay, finally, then we look for asymmetry in charge and if asymmetric equals polar. Once you've found if something's polar, it's very easy after that. Because if it's non-polar, it'll be dispersion. If it's polar, it doesn't have an N or F bonded to a H. Like, they're the rules. So the hardest part is determining whether or not something's polar. Do you want to do one as an example? I'll do one not on there as an example. Leave those ones for you. So let's say we've got oxygen. What do you want to bond oxygen with? Sorry? Magnesium's a metal. You've got to go non-metals. Oxygen and fluorine. Yep. Oxygen needs 2, fluorine needs 1. I need 2 fluorines. So it'll be OF2. Okay, so oxygen needs to give away 2, but fluorine only wants 1. So they have to be single bonds. Oxygen has 6 electrons in its outer shell, so 1, 2, 3, 4, 5, 6. And fluorine has 7 electrons in its outer shell. 1, 2, 3, 4, 5, 6, 7, 8. Why did I count that one? I don't know. Yep. So the valence structure should be, okay, now if you look at the tug of war of electrons between fluorine and oxygen, which one wins? Fluorine, very good. Fluorine's closest to fluorine. Okay, so that'll be delta negative. Now, can I cut it so that it's asymmetric in charge? I mean, if I cut it this way, it's not going to be asymmetric in charge, but if I cut it this way, it'll be positive and negative. Therefore, it is polar.
So it's just, pretty much just less positive and more negative.
Yeah.
It's not really, yeah.
No, it's just more positive and more negative on the other side. Yeah. So really it's all about asymmetric charges. So if you've got something with positives all around it, it's going to be non-polar. Okay, so then you go, is it an N or F bonded to a H? No, there's no H. Where's the H? So it's dipole-dipole. So it's really easy once you found out if it's polar. So why don't you guys have a go at those 5?